Okay, so the reason I'm here is to talk about my experience leading an Agile team of engineers at Yahoo from zero experience with Scala, and then learning Scala and getting to deliver a successful product. All of that like over a year, and how Scala really resonated with Agile core principles that we have. And so I'm going to try to put some arguments of why Scala is great for Agile. Okay, so Agile is like a pretty broad term. Just a show of hands here, like who works in an Agile team or use Agile methodology over here? Almost everyone. We usually define Agile as like the set of practices or methodologies that falls into this umbrella. It's a pretty big umbrella, Agile. So I can say like TDD, XP, Scrum, Kanban, right? And then some teams use a combination, a subset of this or that, and maybe some modifications. But for the purpose of this talk, you're going to go into the core values of Agile, which is written in the Agile Manifesto. And then those core values kind of give the vision for all the practices, all the different methodologies of Agile. They kind of follow this vision of the core values. We're going to focus on the fourth one, which is responding to change over following a plan. The reason being is that though this particular value kind of it gives much more meaning for a programming language to fit well there, right? A programming language to be able to respond to change very effectively. But before I do so and talk about Scala, I'm just going to give like a little note about the first value, which is individuals' interactions over processes and tools. Scala, of course, is a tool. It's not just a tool, it's an amazing tool, but a tool nevertheless, and is under like individuals and processes. So, interaction, sorry. So, what I mean is that Scala is not a necessary condition for Agile, of course. And not adopting Scala is not, it doesn't mean they're going to be Agile, but Scala is very much aligned with Agile. It's not going to be in a way at all. On the contrary, it's going to help you to really deliver fast, respond to change, and all the Agile core values. Okay, so back to responding to change over following a plan, which is the core of this talk. I want to try to paint a picture of three pillars that we think a good programming language has to have in order to be able to respond to change effectively. So this is like the overall picture that I'm trying to paint here. And the three pillars are key characteristics that I'm going to try to make an argument for that a language has to have in order to be Agile, to be considered like an Agile language, and therefore support the team to be able to respond to change effectively. Now when we talk about change, like software code change, we kind of categorize in two different broad kinds of change. Of course there's much more, but just trying to roughly categorize into there's specification change, like feature changes, when your product owner or customer wants a new feature, or you have a feature in the backlog, or you have a feature that needs to be changed because we never like plan everything from the beginning, like things change, like a business changes, right? And there's also an important one, maybe like as important or more important, which is refactor. Refactor is critical when, especially when we don't know about the feature and you can't plan the perfect architecture from the start on your project, because when you start adding new features, you start changing features on the way over time, your complexity gets more and more unmanageable. So you need to stop and refactor to tame the complexity, to change the way that you structure your code, to change the way that to align your components so that you can continue to add more features over time, right? So that's we all think that's the core of the reason for the refactoring. In fact, Agile really enforces put refactoring like in a special place. If you think about TDD, refactor is the third step. After writing the test and writing the code, you have to refactor to like manage complexity and make it more generic and all that stuff. But we suck at refactor. When I look back at the projects before I adopted Scala, like we used to work in Node.js and PHP for a while as well. After a few years working on this like massive code base, it's always like we have this piece of code or module that we are afraid to touch, because refactoring that is going to cause so many bugs, even if you have tests. And so we just like leave it there, and then hopefully we're going to work in something else and leave for someone else to handle that, or maybe get to write this thing from scratch, and that'll be fun anyway. So why is that refactor is much more risky in terms of introducing bugs than actually adding new features? And the reason being, I think, is that effective refactor touches globally in your code. You have to change a lot of contracts, a lot of components in order to make an effective refactor. Meanwhile, adding new features is mostly like a local thing. You just add a new business logic, and you plug in there or here like a new business logic, or just change a particular like a particular feature locally. But refactor is global by nature, and global change is involving like multiple components, breaking a bunch of contracts, like redoing stuff, and you always have something that you left out. So what is like an important refactor tool that we need to have, like a safe refactor tool? I argue that a safe refactor is a refactor that allows you to help you, it helps you to avoid accidental contract breaking. So it's always about contracts. When you have multiple components, there are implicit or explicit contracts between the components. And then changing those components, how they talk to each other. There's changes that you intended, and you change the contract, but there's changes that you left, you kind of accidentally break, and then you introduce a new bug. So how can we enforce the contracts better? And there's types, type systems, and there's tests. But we need, I mean, why not both, right? So we come to the conclusion that having a strong type system is crucial to be agile. Like you need to have that to be able to respond to change effectively. So therefore, our first pillar on painting that picture is typed. We need a type language. Dynamic is a misleading name. It kind of fits with agile. Okay, yeah, well, of course we want to be agile, and dynamic seems like a pretty good word. But dynamic is like unitype. That means that all the contracts are the same, right? So we need the type system to help us to enforce the contracts. It's super important. So that is our first pillar there. Okay, so let me talk about the expression problem. How many of you are familiar with the so-called expression problem? Okay, like not like a small group. So this is like it's an interesting problem in programming language design that shows an asymmetry between functional design and object-oriented design. And it kind of concludes that neither design can really solve the problem very well. There's always a trade-off. So just to give a concrete example here, imagine that you have an abstract type, like a 2D shape, and then you have concrete instantiations on that. For example, like a circle or a square or a triangle, right? And then you have operations on that, like an area or a perimeter. Now, a question for you guys: how would you model that in a functional programming language? This particular problem. I'll give you guys a sec before I move to the next slide. I hope I match your expectations on what you have in your mind. So in functional paradigm, this is a pseudocode, by the way. We usually model this kind of problems by having like an algebraic data type, and then you have constructors for each one of them, like case classes, case of Scala. And then operations are just functions that have a case analysis for each kind of constructor. And then you have the specific computation for each of the cases, right? So that's the way that we solve this problem, like using function design. How about object-oriented design? I'll give you guys a sec before I move to the actual solution here. So that's one solution. So you have there an abstract shape, abstract class, that you define all the abstract methods of the operations. And then you have the actual concrete implementations of it, right? In this case, like square and circle, and then you have all the operations concretely implemented for each. Now, there's an interesting asymmetry between these two ways to solve the problem. If you go back, in this case, we put all the data together, but the operations are separated, right? In the second case, in the object-oriented, we put the operations together, and the data is kind of spread around, separated. And that leads to different ways that these two ways to solve a problem, to write code, respond to change, right? Because they solve the same problem. If you just write the code and let it run in production, it just works, so it doesn't matter. But how about when you have to change this, like responding to change, you know? They have a different behavior, actually, when programmers try to change this code. Just categorizing the change in type 1 and type 2. So type 1 is when you're adding a new data type or changing an existing data type. For example, you're adding a triangle. Type 2 is when you're adding a new operation, like you're adding like a perimeter, for example. Now in the functional paradigm, adding a new data type is hard because although you can just add a new constructor there in your data definition, you have to go over each of the functions, right? And add a new case in your case analysis there, if you want to be total. I guess we all want to be total. So it's global. And the reason global is hard is because your operations can be spread around the code everywhere. You may forget something. And also because it's more work for the program. You have to remember where to look and all that. It can get very complicated for more like real case examples, right? Real world examples. But type 1 is easy in the object-oriented paradigm because all you have to do is just implement a new class of inheriting the base class and just write all the operations right there in the same place. It's local. Conversely, the inverse thing happens when there's a type 2 change. When you have a new operation in the functional paradigm, it's actually easy because all you have to do is write a new function right there. Write a case analysis for all the constructions that you have. That's it, right? Meanwhile, in the object-oriented paradigm, type 2 is hard because you have to go over all the classes, all the implementations of the classes, and add a new method there. So it seems that we don't have any choice. Like there is no way to solve this problem very well. But over the years, and this is debatable, but in our group, we are part of an organization that's doing innovation consumer products. The vast majority of changes that we have is changes in business logic. I know you guys relate to that. Mostly our projects start by, and we want to move super fast because we want to get into the market as soon as possible with an MVP to test our hypothesis of a product that we're trying to create. If we have a lot of users, we have engagement, then we continue to invest on that. Otherwise, we just stop and move to the next thing. For this kind of projects, we observe that usually we define data model at the beginning, and then we may add changes on that later, once in a while, not so often. And a lot of times we don't have a data model that we need to build ourselves at all. We usually do a mashup of stuff. It's all pure business logic. And business logic changed a lot when trying to do innovation consumer products because we're doing like A/B experiments all the time. There's buckets, you know. You launch something, you kill super fast. You have a new idea and then you try. And new ideas are usually business logic changes. So therefore, the thing that we conclude from that is that we mostly have type 2, which is adding new operations. And type 2 is easy in the functional paradigm. So adopting Scala, we saw that, wow, like we have so much easier now. Like everything that we do is local. There is no need for us to go like across the entire code base to change stuff. Like just add a new thing and then it's easy to reason about the code. It's local. Anyway, it makes life much easier. So the second pillar for an effective language here is that we need functional. We need the ability to write functional code, functional design. I'm not saying that we need like a purely functional language or anything like that, but the more that the language, the syntax allows us to use the functional paradigm, the better for the particular applications that we write. So that's our second pillar here. Okay, so let me talk about these two different kinds of ways to solve a problem. There's a style of solving a problem that we're all used to it, which is the imperative style or statement style. And there's expression style, which is a more functional approach where you have a dependency between values, and the functions are more like pure functions that doesn't cause any side effect. They solve in this particular case here, they can solve the same problem anyway. In this case, I'm just have a constructor and then I'm doing 3 changes in the data structure and then returning the data structure modified. Now, if you write this code once and never go back to it, It's fine. It doesn't matter. They do the same job. But how about when you expose this to programmers that go there and try to change stuff? I like to think of programmers as random stuff that go there in your DNA code and do random mutations. They go there, they're trying to achieve something, but they can just swap things around, replace something by something else, not intended. They're just causing mutations there. We want to protect ourselves against unintended mutations. The analogy goes as far as this in code in comparison to biology, because in biology mutation can lead to evolution, but in here can just be a disaster. But think about the kinds of changes that we can have, that a programmer can go and do there. He can go and change the order of a statement, right? You can try to replace a statement by a cache that apparently is doing the same thing. Or programmer can go there and try to optimize and do concurrency, right? Now in statement, you cannot, by default, infer that you can do all this stuff. You cannot change the order. You cannot assume that you can put concurrency there. Neither you can just replace a computation or run a computation twice, right? It can be disastrous. Meanwhile, in the expression style, that you have referential transparency, it's much easier to read the code and see exactly what you can do, and the compiler can help you a lot. If you change the order, the compiler can help you to decide if that's what you want, or if you're replacing a computation by a cache, you can do it, as long as you have the same value. Or if you run the computation twice, that's fine as well. So the expression style on the right is much more resilient to change. It's much more able to respond to change effectively, because it helps the programmer to read and reason about the code, to see like what's going to happen if I change this, or what changes that I can do. You know, everything it looks that I can do, I can. And also helps you if you're trying to do an unintended change. We'll have to keep you on track and say, hey, do you want to? You really wanted to do that? You're breaking a contract, and then you can decide. So what I mean is that refactoring imperative style statements is really like stepping on eggs. You need to know about the underlying stuff that's going on, the side effects. Like you have a procedure that's been called. Anything can happen there. You can have side effects in the next procedure. So the order matters. You can replace that by something else. You can work concurrent code there. So extremely hard. So we learned that our third pillar is really immutable data structures. We have to have that. We have to have efficient immutable data structures in a language for us to be effective. So Scala really helps with that. Of course, Scala has much more than immutable data structures to be able to write code in an expression style. For example, the if condition is expression. It helps you to, the types also helps you to avoid like control breaks and all that. But I think the core of it is immutability, really, like allowing you to really put the side effects in its own corner and isolate that, and to be able to write as much as you can business logic without side effects. So there we have our three pillars over here. A type programming language, a functional programming language, and immutable data types. That is really like the pillars that support an Agile language. And Scala is the Agile language of choice, because there's many options, but mainstream-wise, if you think about like, and JVM support is really important for us because we have legacy code in Java. So it really fits the bill there. It has these three key characteristics that supports responding to change very effectively. Therefore, an Agile team. So that's my talk, and that's why Scala is great for Agile. Thank you so much. We have 5 minutes for any questions.
I've got a question here. Can you expand on how you extended your legacy Java code base with Scala? Just talk us through what that experience was like.
Sure. Actually, it was not as complicated as some cases that I'm seeing. We never had to actually have hybrid code, you know, compiling to bytecode and running to the same component together. Usually, the integration was library-based or microservice-based, so it was very straightforward. At Yahoo, we have a bunch of stuff in-house, security systems, stuff for parsing cookie, for example, in Java, in a variety of components like accessing the user database and all that in Java. That is a library, and it was well designed in a sense because the packages are all libraries, and then we just importing the code and having a wrapper of the types that we want over there. So it was pretty straightforward. I think maybe in a few situations here and there we actually have to copy and paste the code from Java to Scala that's doing something important. And the IDE helps actually. IntelliJ you can just copy and transform it to Scala and then just refactor a little bit to actually to be more idiomatic. So that was like just a few ad hoc situations. Yeah. Any other question?
Thank you.
Thank you.